To this point, we've been discussing puzzles in pure logic. With this lesson, we'll start looking at puzzles drawn from other parts of mathematics. And one of the most puzzling of all mathematical topics is probability. Now, as we go along, we'll carry out a few calculations, but mostly our goal in this lesson is to learn how to think clearly about probability in general. In the next lesson, we'll look at some fancier topics related to this subject. As usual, let's dive right in with our opening puzzle. Here we go. Suppose you have an ordinary deck of 52 cards. We'll assume that the deck is well shuffled, meaning we have no idea at all about the arrangement of the cards. What's the probability that the top card is the ace of spades? Well, actually, that's not really so difficult. You'd probably say that since there are 52 cards and only one ace of spades, the probability is just 1 out of 52. And you'd be right. But that's not really the puzzle. That's just the warm-up. So here's the actual puzzle. Suppose you have two well-shuffled decks of cards. You turn over the top card on each. What's the probability that at least one of those cards is the ace of spades? At first, that also doesn't sound too difficult. You might reason that the probability of getting the ace of spades on the first deck is 1 out of 52, and that the probability of getting the ace of spades on the second deck is also 1 out of 52. So the probability of getting the ace of spades on one or the other is just the sum of those fractions. That gives us 2 out of 52, which is the same as 1 out of 26. But by this point in the course, you probably know to smell a rat. If the puzzle were really that simple, I wouldn't have included it. So I'll tell you that the answer is not 1 out of 26. There's a subtle point that we haven't yet considered. We'll return to this in a few minutes. First, let's talk a bit about probability. As a branch of mathematics, it's very strange. Mathematics is about precision and predictability. We write down equations that tell us precisely what will happen when we carry out an experiment or when we measure some physical process in nature. But probability is about chance and randomness. It's about things that are inherently unpredictable. Those don't seem to be compatible. The great philosopher Bertrand Russell captured this seeming contradiction very well when he said, "How dare we speak of the laws of chance? Is not chance the antithesis of all law?" Even among mathematicians, it's relatively recent that probability has received a place of honor. Its origins come from trivial problems of interest to gamblers, which, in the ivory towers of elite mathematics, tended to give the whole subject a bit of an odor. As recently as 1866, the British mathematician John Venn, for whom Venn diagrams are named, could say, "To many persons, the mere mention of probability suggests little else than the notion of a set of rules, very ingenious and profound rules, no doubt, with which mathematicians amuse themselves by setting and solving puzzles." And yet, reasoning carefully about uncertainty is important for everyone, not just academics and scholars. We all have to assess risk and to decide on courses of action, even in the face of uncertainty about what will occur. And as we shall see later in this lesson, a failure to assess probability carefully can sometimes lead to harmful consequences. Okay, let's return now to our opening problem. We have two well-shuffled decks of cards. We turn over the top card on each. What's the probability that at least one of them is the ace of spades? As we've said, the obvious answer is that since the probability is 1 out of 52 for each deck by itself, then the total probability is 2 out of 52, which again is 1 out of 26. But to see that this can't be right, suppose that each deck has just two cards. Let's say each deck has the ace of spades and the king of hearts and nothing else. Let's try our reasoning again. The probability of getting the ace on the first deck is now 1/2, since there are two cards and one is the ace. For the other deck, we also get 1/2 for the same reason. If we stick to our original logic, then we now say the probability that at least one is the ace is 1/2 plus 1/2, which is 1. But a probability of 1 means that we're certain to get an ace, which is clearly not true. After all, we might get the king on each deck. So something is wrong. But what? The problem is that we've overlooked something important. Specifically, we don't win quite as often as we think we do. Sometimes we get the ace of spades on both decks, and that means we waste one of our wins. Think about it this way. Imagine playing a game where we shuffle the deck and flip over the top card. We do this over and over again. If we get the ace of spades, then we win. Clearly, we're not going to win very often, just 1 out of every 52 times on average. Now suppose we play with 2 decks simultaneously. If we get aces on both of them, then we've wasted one of those rare and precious wins. That means that to find the probability of getting the ace of spades on at least one of the decks, we find the probability for each deck by itself, and then we have to subtract off the probability of getting the ace of spades on both decks. Now, it's a basic fact about probability that to find the chances of 2 independent events happening simultaneously, we just multiply the individual probabilities. In this case, we would get 1 out of 52 times 1 out of 52, which is 1 out of 2,704, 2704. So the probability of getting the ace of spades at least once is 1 out of 52 plus 1 out of 52 minus 1 out of 2,704, which works out to be 103 out of 2,704. This takes some getting used to, so before moving on, let's go back to our decks with just 2 cards each. Following our logic, the probability of getting the ace on either deck by itself is 1/2. Therefore, the probability of getting the ace on both decks is 1/2 times 1/2, which is 1/4. So the probability of getting at least one ace will be 1/2 plus 1/2 minus 1/4, which is 3/4. And in this case, we can check that this is correct by quickly listing all the possibilities. There are 4 ways the cards can come up: ace-king, king-king, king-ace, or ace-ace. And now a quick count shows that 3 times out of 4, we get at least one ace. Very nice. Probability can be maddening. Even scenarios that seem incredibly simple can lead to surprising complications. Try this one. You have a chest with 3 drawers. One contains 2 red socks, one contains 2 blue socks, and the other contains 1 red sock and 1 blue sock. Of course, you don't know which drawer is which. Blindfolded, you reach into one of the drawers at random and pull out one of the socks. It turns out to be red. What's the probability that the other sock in the drawer is also red? Pause the video here if you want to think that over. That doesn't really seem so difficult, does it? We have 1 red sock. That means we definitely didn't reach into the drawer with 2 blue socks. We were either in the drawer with 2 red socks or the one with 1 red and 1 blue. It's 50-50 between the 2 of them. In one case, the other sock is red. And in the other case, the other sock is blue. So the probability that the other sock is red is just 1/2, right? It seems so reasonable, so plausible. But this is probability, so it's a pretty safe bet that our first instinct is wrong. You can easily simulate this experiment on a computer or by using red and black playing cards. If you do the experiment over and over again, you'll find that actually the other sock is red 2/3 of the time and not 1/2. The other sock is red a lot more often than you think. In a moment, we'll try actually calculating the right answer. But first, let's try to understand in general terms what went wrong. Which step of our argument was not correct? The first step is fine. We definitely did not reach into the drawer with 2 blue socks. The error was actually in the next step. It's definitely not 50-50 between the red-blue drawer and the red-red drawer. Look at it like this. We'll choose the red-red drawer roughly 1/3 of the time. But once we choose that drawer, it's a sure thing that we'll pull out a red sock. On the other hand, we also choose the red-blue drawer roughly 1/3 of the time. Having chosen that drawer, however, it's now just 50-50 whether we'll pull out the red sock or the blue sock. Do you see the point? Reaching into the red-blue drawer and pulling out the red sock requires that we get lucky twice. We have to pick the right drawer, and then we have to pick the right sock within that drawer. But reaching into the red-red drawer and pulling out a red sock only requires that we get lucky once. We again have to pick the right drawer, but once we do that, we already win, so to speak. That means that pulling out a red sock is far more likely to occur when we've reached into the red drawer than when we've reached into the red-blue drawer. We can be more precise. If we reach into the red-blue drawer, the probability of pulling a red sock is 1/2. But if we reach into the red drawer, the probability of pulling a red sock is 1. It's a sure thing. So when we pull out a red sock, it's twice as likely that we're in the red drawer than that we're in the red-blue drawer. And that means that the probability the other sock is red is twice the probability that the other sock is blue. We must conclude that the other sock is red 2/3 of the time and blue 1/3 of the time. Again, that takes some getting used to, so try just listing all the possibilities. In the red drawer, let's distinguish the two red socks by calling them red 1 and red 2. Then there are really only 3 possibilities for pulling out a red sock. 1, we reached into the red-blue drawer and pulled out the red sock. In this case, the other sock is blue. Option 2, we reached into the red drawer and pulled out red 1. The other sock is red 2. And option 3, we reached into the red drawer and pulled out red 2, so the other sock is red 1. And there you have it. In 2 out of 3 cases, the other sock is red. Very nice. Now, up to this point, you might be thinking that John Venn was right. Maybe probability is just for amusing puzzles. But actually, you'd be wrong, because this sort of reasoning comes up all the time in daily life. So let's try something a little more applied. You're at an airport, having just landed after a long and tiring flight. You're standing at the baggage carousel waiting for your bag to appear. What percentage of the bags need to have appeared before the probability is greater than 1/2 that the airline has lost your bag? In other words, when should you start to worry? If you want to have a go at that one, then pause the video and think it over. I suspect most people start to worry pretty early. I know that when I first started flying, I'd start to get that sinking feeling after just a few bags had shown up. But having learned some probability theory, I now know that that feeling is not really rational. Let's see if I can convince you of that. Now, if we really want to calculate an exact answer to this, then we need a piece of mathematical machinery known as Bayes' theorem. We'll have a look at that in our next lesson. But in keeping with our present theme of thinking clearly about probability, let's see if we can arrive at an answer while doing the absolute minimum amount of calculation. So there you are, standing at the baggage carousel, waiting for your bag. Let's say you see that roughly half the people have already left, so you take that to mean that half the bags have already arrived. Should you start to worry? Well, let's see. There are 2 possibilities at this point. It might be that your bag has not yet arrived because it's among the second half of the bags. Or it might be that your bag is actually lost. Now, just by chance, you'd expect that your bag is in the second half about half the time. But even the worst airlines don't lose half of the bags that they check. Even in the days before barcodes and computer scanning, an airline couldn't stay in business with such a poor track record. So, with half the bags having appeared, we really shouldn't start worrying. What about after 3/4 of the bags have arrived? At this point, a large majority of the people have left to seek ground transportation, while just a few stragglers remain around the carousel. Should you be worried now? I don't think so. Just by chance, your bag will be among the last quarter roughly 1/4 of the time. Do we think airlines lose bags 1/4 of the time? That still seems pretty high. Though we might have to force ourselves to stay calm, we should still think it's far more likely that our bag is just near the end of the line and not on its way to some other city. Just how often do airlines lose a bag? Well, it turns out that nowadays, the worst, most unreliable airlines lose less than 2% of the bags that they handle. Let's round up to 2%. That suggests that fully 98% of the bags would need to arrive before we consider it 50-50 that the bag is lost. In other words, among all the times that your bag is not among the first 98% of the bags, about half the time it's among the other 2%, and about half the time it's actually lost. In other words, when should you seriously start to worry that your bag is lost? When all of the bags have arrived and yours is not there. Not one bag sooner. In the case of a baggage carousel, the stakes are pretty low. If you don't know your probability theory, then you'll worry a bit more than you need to, but no real harm will be done. Sometimes, though, the consequences are a lot more serious. Failure to understand probability can sometimes lead to some very bad consequences indeed. Let me give you an example. Suppose there's a disease going around that affects roughly 1 out of every 1,000 people. There's a test for the disease, which is 95% accurate. It never gives a false negative. If it says you're clean, then you're clean. But in 5% of cases, it gives a false positive. Let's say you take the test and it comes back positive. How worried should you be that you actually have the disease? I'm presenting this as a puzzle, but it's actually a fairly realistic scenario. And fair warning, research has shown that a distressing percentage of doctors get this one wrong. I suggest pausing the video here and taking a stab at this yourself. What answer did you come up with? If you answered that you should be pretty worried, then you probably reasoned that 95% accurate is pretty darn good, and that's the end of the story. But one more time, that reasoning overlooks something important. We need to pay attention to the lessons of our previous two examples. In the problem with the socks in the drawers, we saw that drawing a red sock was far more likely to occur when we were in the red drawer than in the red-blue. In the baggage carousel problem, regardless of how many bags have appeared, your bag is pretty much always more likely to be later in the line than it is to actually be lost. We need similar reasoning here. There are two ways to get a positive test result. It could be that you actually have the disease, but it can also be a false positive. Now, the probability that you have the disease is 1 out of 1,000, which is 0.1%. But the probability that you got a false positive is 5%, which is 50 times greater than the probability of actually having the disease. Let's put some numbers to this. Suppose you sample 1,000 people. Then on average, we expect 1 person to have the disease and 999 to be healthy. That 1 person will receive a positive test result, since the test never gives a false negative. But 5% of the 999 healthy people will receive a false positive result, which comes to just under 50 people. We'll round it off to 50. So out of 51 positive test results, just 1 is real, which corresponds to a roughly 2% chance that you actually have the disease. In fact, even if I had said the test was 99.9% accurate, it still works out to a mere 50-50 chance that you have the disease. Since the disease only affects 1 person out of 1,000, it's pretty much always more likely that you got a false positive than that you actually have the disease. At this point, we're in danger of going too far the other way, by concluding that our test, which was 95% accurate, remember, is actually worthless. But this conclusion is also mistaken. After the positive test result, the probability that we actually have the disease jumps from 0.1% to 2%, which is a 20-fold increase. That's nothing to be dismissive about. The fact is, nearly everyone gets the right test result. Most people get a negative result and are actually negative. So the test is useful, but far from definitive. Now that we've seen some of the basics of probabilistic reasoning, let's wrap this up with 2 more puzzles for you to try on your own. In each case, focus on seeing the logic behind the answer rather than actually trying to calculate anything. We'll present both puzzles first, and then their solutions. Here we go. Here's the first puzzle. The World Series is played between the Yankees and the Dodgers. Each team has the same small advantage when playing at home, but otherwise the teams are equally matched. The series starts with 2 games at Yankee Stadium, and then up to 3 games at Dodger Stadium, and then 2 more games at Yankee Stadium if those games are needed. Remember that the World Series is a best-of-7 competition. The first team to win 4 games wins the series. Suppose I tell you that the series ended in exactly 6 games. Which team was more likely to be the winner? And finally, here's an absolute classic. You can walk into any gathering of mathematicians and mention the Tuesday birthday problem, and everyone will know what you mean. You meet a person who tells you she has 2 children and that one is a boy born on a Tuesday. What's the probability that the other child is a boy? Actually, to keep with our theme of not wanting to calculate anything, just try to explain why the answer isn't 50-50. Why does it matter that one is a boy born specifically on a Tuesday? Have a go at these 2 puzzles. Pause the video here and come back for the solutions when you're ready. Did you get them? Let's see how you did. In the first puzzle, we had the World Series ending in exactly 6 games, and we needed to determine which team was the most likely winner. To start, it does seem clear that if the series ends in exactly 7 games, then the Yankees would be favored to win because they would play 4 home games to the Dodgers' 3. And if the series ended in exactly 5 games, then we would expect the Dodgers to have won since this time they got the extra home game. But at first blush, it would seem that in exactly 6 games, it's 50-50, since each team then plays 3 home games. Incredibly, this reasoning is not correct. We could certainly arrive at the correct answer by listing every scenario and working out the probability of each one, but that seems awfully complicated. Instead, let's imagine that the home field advantage is enormous, so that the home team is much more likely to win. In that case, if the series ends in exactly 6 games, the most likely scenario by far is that there was just 1 game where the visiting team won. That upset must have occurred among games 3, 4, 5, or 6, since otherwise the series would have ended in 5 games. But it's only when the upset happens in game 6 that we have a scenario where the Dodgers win. Since the probability of an upset is the same in every game, we'd find that the Yankees are nearly 3-1 favorites. Here's a more precise way of looking at it. Suppose we said the series ended in at most 6 games instead of in exactly 6. In that case, we would say that of the potential games played, each team would play at home 3 times, making the odds 50-50 as to who would win. But the chances of either team winning in exactly 4 games is 50-50, since in such a series, each team would play at home twice. If the series ends in exactly 5 games, then the Dodgers have the advantage, since they would be the home team 3 times, while the Yankees would be the home team only twice. But if the Dodgers have the advantage when the series ends in no more than 5 games, but it's 50-50 when it ends in no more than 4, then it must be that the Yankees have the advantage when the series ends in exactly 6 games. Which brings us to the infamous Tuesday birthday problem. A woman has 2 children, and we know one is a boy born on a Tuesday. What's the probability that the other child is a boy? Now, our first reaction might be to say the answer is obviously 1/2. I mean, seriously, we know that every child is born on some day of the week, so what difference does it make that we know specifically that it was Tuesday? But it does make a difference. In fact, this puzzle is similar to our opening puzzle with the ace of spades and the 2 decks of cards. We saw that the possibility of getting the ace of spades on both decks at the same time meant that we don't win as often as we think we do. Something very much like that happens here. Let's try listing all the ways we can have 2 kids where one is a boy born on a Tuesday. If the first kid is the Tuesday boy, then the other kid can be either of 2 sexes and can be born on any day of the week. That makes 14 possibilities, with the other child being a boy in 7 of them. We would reason the same way if the second kid is the Tuesday boy. Then the first kid can be either of 2 sexes and can be born on any day of the week. This again makes 14 possibilities, with the other child being a boy in 7 of them. This makes it look like the answer really is 1/2. There are 28 possibilities, and the other child is a boy in 14 of them. But I bet you've already noticed what this argument overlooks. One pair got counted twice. Specifically, we double counted the case where both kids are Tuesday boys. That means there are not 14 pairs where the other child is a boy, but only 13. And there aren't 28 pairs total, but only 27. So what's the probability that the other child is a boy? The correct answer is 13 out of 27. Probability takes a lot of getting used to, but it's worth the effort since probability is everywhere. Every time you see a political poll, or learn about the statistical health effects of different behaviors, or even when you hear the weather person say there's a 30% chance of rain, it certainly helps to know a little probability. And what better way to flex your probability muscles than to consider a bunch of fun and clever puzzles? See you next time.